Hello everyone. What I'm gonna do in this video is do some more examples on 6.3 and explain 6.3 in some more detail. Okay, so what you have in 6.3, just a reminder, what we're using is an annihilator method, which is like when we use a method of undetermined coefficients. And also what this does is motivates where our guesses come from in the method of undetermined coefficient. So this is the annihilator method and the method of undetermined coefficients. That's what it's called. Okay, so in the first place, what is this annihilator? So you say a differential operator. So what's a differential operator? The kinds of things we've seen is, for example, if you have d squared minus 2d applied to a function y, what does that do? That's d squared of y minus 2d of y, or let's just put a plus 3 here, plus 3y. What is this? This is y double prime minus 2y prime plus 3y. Okay, so just an example. And this over here is our differential operator. Okay, so what's an annihilator? You say a differential operator A is said to annihilate a function f if A applied to f is the zero function. All right, so a linear differential operator. So we're talking about linear operators. Okay, so what do you mean? Oh, a of y, of course, when you apply a to y, you get some function. So for example, in what we have over here above, we have a of y is y double prime minus 2y prime plus 3y. So a of y is some function. So what we are saying is the differential operator is said to annihilate a function if when you apply the operator to y, you get the constant function 0. So what you mean by this is just applied to any x, you always get 0. That's what you mean. Okay, so example, let's say we have our function y. Let's say y is the function sine x. Can you think of a linear differential operator that annihilates sine x? So So, have you had time to think about this? What kind of operator can you apply to sine x to get 0? Well, that's the same as asking the question, well, what kind of combination of derivatives of y, linear operator, do you need, which has as a solution, so you want that what kind of an operator do you have, and when you apply it to y you get 0 such that y equals sine x solves this. Okay, so what kind of a do you need such that a applied to sine x is 0? Well, when is sine x, for example, you can go to constant coefficient equations. If the characteristic polynomial is x squared plus 1, okay, or the differential operator is d squared plus 1, all right, that is y double prime plus y when you look at d squared plus 1 applied to y double y, you get y double prime plus y. When you look at d squared of plus 1 of y equals 0, which is the same as y double prime plus y equals 0, what function solves this? You know y equals sine x solves this. Okay, so in the above example, y equals sine x. So if y equals sine x, then we know that the linear differential operator that annihilates sine x is d squared plus 1. Okay, or in short, d squared plus 1 applied to sine x, you will get the 0 function. All right. Here, let's take another example. Find a linear differential that annihilates, let's do this, x squared e to the minus 2x. Okay. So you want to find a linear differential operator that annihilates the function x squared times e to the negative 2x. Okay. So you ask yourself, what kind of characteristic polynomial would you need to have such that when you look at the roots and look at what solution you get, one of them is x squared times e to the negative 2x. Well, looking at this, you know this means that negative 2 is a root, okay? And because of this x squared, you know that it is repeated, right? And when it's repeated twice, you have an x. So when you have an x squared, you know it is repeated 3 times. So what do you have? X minus negative 2 cubed. Okay, or that is x plus 2 cubed. That should be the characteristic polynomial. Of course, you could cube it and write it down. So if you want, here, just cube it. You have x cubed plus 2x squared plus 4x plus 8. All right. Or you can write down, that means that the linear differential operator is d plus 2 whole cubed, or d cubed plus 2d squared plus 4d plus 8. When you apply this to the function x squared e to the minus 2x. So, you know, you take the function x squared e to the minus 2x, differentiate it 3 times, plug it in there. Differentiate it twice, plug it in there. Differentiate it once, plug it in there. And then add 8 times the function itself, then you will get 0. So let me just write that down. X squared e to the minus 2x triple prime plus 2 times x squared e to the minus 2x double prime plus 4 times x squared e to the minus 2x prime plus 8 times x squared e to the minus 2x. If you do this, this will turn out to be 0. Okay? So you found a differential operator that annihilates this, and the answer is d plus 2 cubed, or d cubed plus 2d squared plus 4d plus 8. Either ways. Okay, it's the same thing. Okay, so once we have that, now we're going to apply this thinking, this annihilator thinking, to constant coefficient linear inhomogeneous differential equations, okay, of any order. All right, so let's take an example. And here we have y double prime minus 5y prime plus 6y equals cosine 2x. Okay, so let's take a look at this. All right, now we want to solve this constant coefficient inhomogeneous differential equation. Okay, so what we're going to do is first let's take a look at cosine 2x. What operator annihilates cosine 2x? Okay, you know that that means the imaginary roots. So you know that to find the operator that annihilates cosine 2x, you know that you need to look for a characteristic polynomial that has plus and minus 2i as the roots. So you know it should be x squared plus 4 should be the characteristic polynomial. So you know that d squared plus 4, this operator annihilates cosine 2x. Okay, did that make sense? How did I get that? Because if you look at y double prime plus 4y equals 0, you know that a solution to this will be cosine 2x. So if you look at d squared plus 4 applied to cosine 2x, what does that mean? It means that you're differentiating cosine 2x twice, and then you're doing 4 times cosine 2x, and you know that means cosine 2x double prime plus 4 times cosine 2x. You know, because cosine 2x is a solution to this, that means you plugged in cosine 2x in place of y over there, so you should get 0. Okay, I'm explaining more over here because we've just seen one right now and it's been a while. Okay, all right, so one part was let's take a look at the right-hand side and find the operator that annihilates this. Okay, secondly, let's look at the left-hand side and write it down in operator form. So this is d squared minus 5d plus 6 applied to y. All right? Okay, so what I'm going to do is I'm going to write down this differential equation in operator form, and we're also then going to use the information that that operator annihilates the right-hand side. Okay, so y double prime minus 5y prime plus 6y equals cosine 2x. All right, I'm writing it down as d squared minus 5d plus 6y equals cosine 2x. Okay, all right. Now what I'm going to do is so since this side equals that side, you can take both of the sides and multiply them by 8. You can take both the sides and differentiate them. You can take both the sides and add 20 to them. So what we're going to do to both the sides over here is apply the operator d squared plus 4 to both sides. What does that mean in words? I'm going to take both the sides, differentiate it twice, and add 4 times the original. Okay, so let's do that. So I'm going to apply d squared plus 4 to both sides. And this is what I get. Okay, so let's continue. What does that mean? So right-hand side you have d squared plus 4 applied to cosine x. We already saw. What is this? D squared plus 4 is the operator that annihilates cosine 2x, sorry. So you know that this side is 0, correct? And what about this side? This side is just some operator that looks like this. Okay, we didn't study this. This is in chapter 5, but this over here, when you have this, it means that you take y, differentiate it twice, subtract 5 times the derivative of y plus 6 times y, and then whatever you have over there, what you do to that is Once you have that, differentiate that result twice and add 4 times that result. Okay, so it's when you write this down like this, just like we have d squared, that is d composed with d, that is take the derivative and then take the derivative of the derivative. This means that you apply this operator to y, and then you take the result and then apply the operator d squared plus 4 to the result. Okay, but in any case, when you look at this now really, if you actually open it up, you will have what degree differential equation? This will give you second derivative of y, and then you're differentiating it twice again, you'll have a fourth derivative of y. So what this actually will turn out to be, this is a fourth order, or actually this whole thing, this is a fourth order constant coefficient homogeneous differential equation. Okay, and do you know what the characteristic polynomial of this is? Well, we've already seen the characteristic polynomial always matches the operator. The characteristic polynomial is x squared plus 4, or r squared plus 4 if you want to write an r, times r squared minus 5r plus 6. Or actually, let's write the characteristic equation, not the polynomial. Okay, so that's what we have. Now, what do? To find solutions to a constant coefficient homogeneous differential equation, what do? You find all the roots of the characteristic equation. Okay, so let's factor this. Yeah, this stays as r squared plus 4 because that's complex. And r squared minus 5r plus 6. So what do you have? R minus 3 times r minus 2. That part will be there. So you have this. So what are the roots? Roots are plus and minus 2i, right? 2 of those. 2 and 3. Okay, so what's the general solution to this equation? It's going to be, let's write it down. I'm going to start with these two. C1 e to the 2t plus C2 e to the 3t plus C4 cosine 2x plus C5 sine 2x. Okay, all right. So what do we have? This function over here is the solution to this equation above, which is the starred equation. Well, this starred equation is equivalent to the swirl equation above. Okay, so this starred equation what happened? Okay, all right. Now look at the corresponding homogeneous. What is swirl? Swirl says that you have d squared minus 5d plus 6y equals cosine 2x. Okay, that was the swirl equation. Okay, so now take a look at this and look at the corresponding homogeneous one, 5d plus 6y equals 0. What is let's call this triangle. Okay, let's call that the triangle equation. Okay, what's the solution to a triangle equation? So solution to corresponding homogeneous equation is, you know, how do you solve this? You would write down the characteristic equation, r squared minus 5r plus 6 equals 0. You already know. We've already done that as part of this above. So this will be C1 e to the 2t plus C2 e to the 3t. Okay, so solution to the corresponding homogeneous equation is this. Okay, so what do we have now? Let's go back to the solution that we found to swirl. Okay, the original problem. Okay, we found a solution to swirl by modifying it to a homogeneous equation, star, and finding a solution to star. Okay, so look at this solution here. Out of this solution, this part solves the homogeneous. So, since that part solves the corresponding homogeneous equation, we know that the form of particular solution to the original equation is in fact what's left over, and that is C4 cosine 2x plus C5 sine 2x. Okay? And now to actually find what C4 and C5 are, we'll have to plug it in there. So we'll plug it in. Let's call this YP. YP prime will be minus 2C4 sine 2x plus 2C5 cosine 2x, and YP double prime will be minus 4C4 cosine 2x minus 4C5 sine 2x. Okay, plugging all these in there, you have minus 4, plug these in, what is this? Just reminding you, that's just y double prime minus 5y prime plus 6y equals cosine 2x, okay? So plugging these in, what do we get? We'll get minus 4c4 cosine 2x minus 4c5 sine 2x minus 5 times yp. So let's just leave it in parentheses for now. Plus 6 times the original and you need this to be cosine 2x. Okay, so we'll collect all the cosine terms and then collect all the sine terms and leave those separate. Okay, so what do we have for cosine terms? Minus 4c4 plus 10c4. Okay, I'm sorry, not 10c4. You'll have minus 10c5 plus 6c4 cosine 2x plus, let's write down the coefficients of sine, minus 4c5 plus 10c4 plus 6c5 sine 2x. Okay, and this needs to be 1 cosine 2x plus 0 sine 2x, right? Of course, cosine 2x is 1 cosine 2x plus 0 sine 2x. Okay, so that tells you, just putting this together, that should equal 1, and this should equal 0. So just put it together. 2c4 minus 10c5 is 1. And what do you have? 10c4 plus 2c5 is 0. All right, multiply this by 5. You get 10c4 minus 50. C5 is 5, and you have 10c4 plus 2c5 is 0. So subtract one from the other, and you'll have minus 48. C5 is 5, so C5 is 5 over 48. Okay, and then just plug it in there. You'll have 10C4 is minus 2C5 is minus 10 over 48. And so you have C4 is negative 1 over 48. Okay, so that tells you that YP, a particular solution to the inhomogeneous, or will be minus 1 over 48 cosine 2x plus 5 over 48 sine 2x. Okay, that solves the inhomogeneous equation. Okay, so what did we do? Just quickly review. We looked at the original equation. We wrote it down as an operator. We looked at the right-hand side inhomogeneous term, found out what operator, linear differential operator, annihilates that. Applied that to both sides, so then the right-hand side becomes 0, and what you have remaining is just a constant coefficient, fourth order linear homogeneous differential equation. We found the solution to that by looking at the roots and everything, and the solution to that had this form right here. And we stared at that and saw, by looking at the corresponding homogeneous equation to the original, we saw that this first part solves the corresponding homogeneous to the original equation, this in the box. So what's remaining is what will solve the inhomogeneous part. So solution to corresponding homogeneous is this. So whatever is remaining is that form of a particular solution to the inhomogeneous equation. Then we took that, plug it in to find the coefficients. Sometimes in some of these problems, you're not even asked to find these numbers. All you're told is to use the annihilator method to find the form of a particular solution. Okay, so we're going to do that now. Just going to find the form of particular solutions and then plugging in to find the unknown constants you've done in the method of undetermined coefficients. Okay, so let's once again look at a very example very similar to what we have, and this is number 21 from the book. Okay, we have u double prime minus 5u prime plus 6u is cosine 2x plus 1. Okay, so this is very similar. Over there you had y's instead of u's. That's okay. And over here you have cosine 2x, but you also have a plus 1. So, okay, write this down in operator form. D squared minus 5d plus 6 of u equals cosine 2x plus 1. Okay, what was the first step? We write it in operator form. Next, let's look at the right-hand side and think about what operator annihilates that. Okay, we want to annihilate this sum. Okay, so we know if you look at this part, d squared plus 4 annihilates that. Okay, what about the constant 1? What can you do to the constant 1 to get 0? So what operator can you apply to 1 and get 0? Well, if you just differentiate the number 1, you will get 0, right? Okay, all right. So put these two operators together as a composition. Okay, so let's look at d squared plus 4 composed with d, and in operator notation, that's just d squared plus 4 times d. Okay, take a look at this operator. And let's apply it to the sum cosine 2x plus 1. Okay, what will that be? That'll be d squared plus 4 times d, or which is composition applied to cosine 2x, plus d squared plus 4 times d applied to the number 1. Okay, so this is composition for operators. You know, composition means you write it as multiplication, but you know d squared means d of d. So apply d to the function and then do d of what you have. Okay, so this one's easy. What do? Okay, so first you do d squared plus 4. First you do d of 1. What is d of 1? That's 0. So d squared plus 4 of the function 0. If you take the function 0, differentiate it twice, add 4 times the 0 function, of course that's going to be 0. So that part was easy. How about this? D squared plus 4 of d of that. Well, you know what you can do? You can take these two, the composition of different linear differential operators, you can do in any order. And that is something that was covered in chapter 5, which we didn't do. D squared plus 4 of d, this is the same as first apply d squared plus 4 to cosine 2x, and then you apply d to that. Okay, and that will be what? So that is d of d squared plus 4 applied to cosine 2x. But we already know d squared plus 4 annihilates cosine 2x, so that is just 0. What is the derivative of 0? That's just 0. So what you have over here is that if you look at d squared plus 4 composed with d and apply it to the sum, you got 0 plus 0, so it is 0. So if you have a sum of functions and you want to find a linear differential operator that annihilates the sum, just find differential operators that annihilate each one. Okay, remove anything in common. We'll talk about that in a second. And just multiply them. And then you'll have a differential operator that annihilates the whole sum. All right. Okay, so now we know that d squared plus 4 times d annihilates both sides. Annihilates the right-hand side. Okay, so apply the operator d squared plus 4 times d, and if you want, you can write d cubed plus 4d, that's fine, to both sides. Okay, so what do you have? You have d squared plus 4 times d squared minus 5d plus 6 applied to a function y is d squared plus 4 times d applied to cosine 2x plus 1. We already saw that that is 0. So what we're left with is a constant coefficient linear differential equation to solve. Okay, you know when you multiply this out or start applying the d's to the function y, apply d squared plus minus 5d plus 6 to y, and then differentiate that, and then apply d squared plus 4 to that, you're going to get this whole string of derivatives of y with constants in front. Okay, it'll be a homogeneous linear differential equation with y as the function. Okay, what's the order? I'm just telling you, look at it and observe what's the order. That's going to give you second order, that applied, then you apply d to that, that'll be third order, and then you apply d squared plus 4 to that, that'll be fifth order. So it's a fifth order constant coefficient linear differential equation. Okay, what's the characteristic equation or auxiliary equation, whatever you want to say? R squared plus 4 times r squared minus 5r plus 6 equals 0. So what are the roots? You know this is r minus 3 or I wrote r minus 2 before, so let's do the same. R minus 2 times r minus 3. This is r, and this is r squared plus 4. Let's just write it like that. So what are the roots? Plus 2i minus 2i, 0, 2, and 3. Okay, so what's a general solution to star? Will be C1 cosine 2x plus C2 sine 2x plus C3 e raised to 0x or t. Well, that's just 1, so it's just C3. That's just 1, so you just write C3 plus C4 e raised to 2x plus C5 e raised to 3x. Okay, so this is GS2 star. All right, but star is equivalent to the original inhomogeneous equation, right? Which is the original inhomogeneous equation? This one right here. D squared minus 5d plus 6u equals cosine 2x plus 1. Or if you want u squared minus 5u prime, u double prime minus 5u prime plus 6u equals this. Okay, so looking at that, the original inhomogeneous equation okay, and then what's a corresponding homogeneous is u double prime minus 5u prime plus 6u equals 0. What is the solution to that? This is solved by over here it is. Let's just write C4 e to the 2x plus C5 e to the 5x. 3x. So this part right here solves homogeneous. So whatever is left behind is the form of solution to inhomogeneous. C1 cosine 2x plus C2 sine 2x plus C3. Okay, and also go back to the original equation. And if you look at this, and if I gave you this problem when we're doing the method of undetermined coefficients, what would you do? First solve the homogeneous, find out what the answers are, and then based on that you make your guess looking at the right hand side, and even then your guess exactly would have been this. Okay, and this actually explains where did that guess come from. The guess came from this annihilated method, and it told us that when it's cosine 2x, we include both cosine and sine. When you have a e to the kt, we'll have a e to the kt, and so on. Okay, so this is the form of a particular solution to the inhomogeneous equation. Okay, all right, so let's do one or two more to make this okay, where we have repeated roots. All right, so let's do number 24. This is theta double prime minus theta equals x e to the x. Okay, d squared minus 1 applied to theta equals x e to the x. Okay, when you mean 1, it just means identity of the function, so it's just the function. Okay, what annihilates that? You know that 1 is a root because it's e to the 1x. But because of this x, you know 1 is repeated. Okay, so it's just a repeated root, repeated twice. So you know r minus 1 squared would be the auxiliary equation of a differential equation to which x, e to the x is a solution. So you know an operator that annihilates that is d minus 1 whole squared. Okay, and you can check what do you have? D minus 1 whole squared applied to x e to the 2, e to the x. What is this? It's just d squared minus 2d plus 1 of x e to the x, or you're differentiating x e to the x twice minus 2 times x e to the x plus x e to the x. What do you get? Well, if you look at the equation y double prime minus 2y prime plus y equals 0, you know that a solution to this is x e to the x. So, of course, when you plug in x e to the x over here, then, oh, there should be a d over here. When you plug in an x e to the x over here, you will get 0, correct? Because x e to the x solves this differential equation. Okay, so an operator that annihilates the right-hand side is d minus 1 whole squared. Okay, so let's write the equation again. D squared minus 1 applied to theta equals x e to the x. Apply the annihilator of the right-hand side to both. So you'll have d minus 1 whole squared. D squared minus 1 theta equals d minus 1 whole squared applied to x e to the x. This, we see, is 0. So now we have our constant coefficient fourth order homogeneous differential equation. And how do we solve it? We look at the roots of the auxiliary equation. Okay, so what is it? R equals 1, 1, and this is R plus 1, R minus 1. So it is 1, 1, 1 repeated 3 times and negative 1. Okay, or if you want, rewrite this as R minus 1 squared times R minus 1 times R plus 1. So R minus 1 cubed times R plus 1, whichever way, it's fine. All right, so 1 is a root that's repeated 3 times and negative 1 is just there once. Okay, so what will be a general solution to this homogeneous equation? It'll be C1 e to the x plus C2 C2x e to the x plus C3 x squared e to the x. Correct? Because it's repeated 3 times, we have this as the part which takes care of the root r equals 1, and then plus C4 e to the minus x. All right, so that's the general solution to the homogeneous. Okay, and go back to the original. So this, you know, is also the form of the general solution to the original equation. Okay, now look at the original equation and corresponding homogeneous equation for the original is d squared minus 1 of theta equals 0. What solves this? It's, you have r minus 1 or r squared minus 1 equals 0, which is r minus 1 times r plus 1 equals 0. So what solves the corresponding homogeneous to the original is e to the x, okay, and e to the minus x. And because of the letters I have up here, I'm going to say C1 e to the x plus C4 e to the minus x solves the homogeneous equation corresponding to original inhomogeneous equation. So when you take this as your guess for the form of a solution to the original, the first term and the last term won't do anything because they're just going to give you 0. Okay, so you know, comparing these two, you know that a particular solution to the original inhomogeneous equation has the form c2x e to the x plus c3x squared e to the x. So this is the form of solution to original inhomogeneous equation. Okay, and if you had done the method of undetermined coefficients, what would you have done? Just go back to the top of the page. You would have said your guess is ax plus b e to the x. Okay, but then you would have seen that b e to the x solves the homogeneous, so you would have put an x out front, so you will have that ax squared plus bx e to the x is the proper form of solution to the inhomogeneous over here, which is exactly what we got. C2x e to the x plus C3x squared e to the x. And you see it's the same. C3 is your A and C2 over here is your B. So if you look on the bottom at what we got over here and compare it to what your guess would have been with undetermined coefficients, it's exactly the same. All right. Yeah, this might seem longer, but this also comes with no prior knowledge of what the form needs to be, or guessing that when you do this differentiation, you get this. This is just, okay, let's look at this. Let's apply an operator that makes it into a simpler equation. So we applied an operator, made it into a simpler equation, found the form of the solution. We know this part and this part solves the homogeneous, so they're not going to help. So the form of a particular solution will just be the center part. All right. So I hope this makes sense to you. And of course, now, once you have this, once you have the form of solution, what can you do? You can plug it into the original and find out what the C2 and the C3 are. Okay, once you have the C2 and the C3, you could plug it back into the general solution for the inhomogeneous. And if you had any initial conditions, you would then have C1 and C4 as unknowns in here, and you would solve for C1 and C4 given theta of 0 is something, or theta prime of 0 is something, whatever, like that. Okay, that is just old stuff. Once you have the form of the solution, then you just do what you did with undetermined coefficients. Okay, so I hope this made sense to you, and that using annihilators, it's not really very different from doing the writing it as a differential operator is not very different from just writing the differential equation. Okay, it's just more convenient to write it as operators, especially when you're using this technique of annihilators. All right, well, I hope this made sense to you guys. Please feel free to email me if you have any questions. And for those of you who have stuck on till now, I'm telling you, I will also change the due date of the homework and push it back some more. I know everyone has a lot going on and a huge adjustment period to this weird situation that we're all in. And I will push the homework date back as well. Okay? All right, guys. I will, hopefully this is enough for you for 6.3 and 6.4 we had discussed before. I've also uploaded the notes to both of those. All right, take care everyone. See you guys.